Hi, Gracie. Hi, Kaylee. I hate you both. Same with you, Maggie.
Okay, so on this vertical motion stuff, so you're going to have two extremes when something's going around in a circle. So at the bottom, your total force is going to be Fc plus Fg. Okay? Now, here's the significance of this. You cannot be in the state of weightlessness at the bottom of the curve. Okay? Because you can't have like a negative value for the force total. Okay? So even if you're just sitting there, and remember, this is what you are going to experience. This is what you are going to feel. Okay? So if I'm just sitting here, at the bottom of the curve, we're traveling on a straight path, I'm just flying level, whatever, then there is no centripetal force. So what I feel is a normal weight. This is what you all have spent your entire lives feeling. Oh, right. So what do you feel right now inside this room? Okay? So if this room started to swing back and forth, okay, at the bottom of that arc, you all would feel heavier, because not only is there the normal gravitational pull that you're experiencing, you would also add to that some additional centripetal force because you're making your body travel in a circular path. Okay? So this is why at the bottom you cannot be in the state of weightlessness. You will always at least be feeling the normal gravitational force. So there's a question about the fighter pilot. Okay? Fighter pilots can withstand at most, like, I think it's what, 9 times their weight and without passing out. Okay? So what we're saying is that when they're at the bottom of this arc, this is what they're going to experience. That's what's going to be that 9 FGs. It's the same thing on all those problems that you worked up on problem number 4. So on number 4, your total force, you started with this, was Fc minus Fg. Okay? So up at the top, what you feel is a fraction of your weight. On that first one, you want to feel like 1/4 Fg equals Fc minus Fg. So it starts the same way. If you're at the top, it's force centripetal minus Fg. If you're at the bottom, it's force centripetal plus Fg. Okay? So that's how you want to start. So if all goes well on number 6, that radius should be something times 10 to the 4th. Okay? Something times 10 to the 4th. On number 4, because the 4a starts wrong, everything is going to be wrong. So that answer to 4a, and this is an ish, should be around like 16 meters per second. Okay? Ballpark, something around there. And then it's going to end up something close to the legal drinking age. Now, bless you. So when you get to question 7 and 8, so here's the basic idea, is that here's this wall, okay, and you're here like this, right? And this is what we tried to simulate yesterday. So oddly enough, we'll use Newton's apple, okay? So if I put this on here, right, and I begin to swing that around quickly, it stays up. But if I slow down, it falls. So what that tells me is that whatever happens has something to do with how fast that thing is spinning, okay? Because if how fast I spun wasn't a factor, then I could slow it completely down and it would still stay there. But obviously if I go fast enough, it stays there, but if I slow down, it doesn't. So what's happening, and here's the best analogy that I can give you, is that you have this centripetal force that's acting inward, you have the frictional force acting up, and you have the gravitational force acting downward, okay? So it's that centripetal force acting upward that's balancing out that gravitational force. But what's creating the centripetal force, the magnitude of that centripetal force, is determining the frictional force. So it's just like if your hands are barely touching because they're not being pushed together very hard, there's not a lot of friction. When you really push your hands together really hard, then there's a lot more friction. So what happens is that you spin faster and faster and faster. That centripetal force is acting inward. You're trying to move in a straight line. So that's what's creating that frictional force, because it's being pushed together and it doesn't want to slide. Okay? And the harder you push it together, the more reluctant it is to slide past. So that's that whole idea when you say, okay, start with this. Mu equals force friction over force normal. Now, I want to look at two different situations with this, and you have to keep these two things straight, because these equations are not on your equation sheet, but you have to know them, this concept for the test. So if Bubba's in a barrel, and that's exactly how the test is, how that test question is going to play out. I'm going to tell you, Bubba is in a barrel, and the barrel is spinning. Okay, it will literally say that Bubba's in the barrel. Okay. So if Bubba's in the barrel, your frictional force has to balance out your gravitational force, and your force normal is acting at right angles to the surface. So that's your centripetal force. So that's mg over mac, masses cancel out, you get g over ac equaling mu. So that's if Bubba's in a barrel like this. Now, in contrast to that, you have a situation where Bubba is moving around in a circle like this, and friction is what's keeping him moving in a circle. So if Bubba is driving his car around a dirt track, okay, so if Bubba's on the dirt track, okay, it's a similar type idea. It's still force friction over force normal. But in this situation, when Bubba's going around in a circle, your frictional force is what's creating the centripetal force. Force normal, because we're on a flat surface, is the same as your gravitational force. So that's mac over mg, masses cancel out. So these are inverses of each other. So if Bubba is in the barrel going around like this, it's g over ac. If Bubba is driving his car around the road, it's AC over G, okay? So they're inverses of each other. So figure out some way to just think that through, okay? Make sure that you understand the difference between those two situations. Okay, so your answer on number 8 for that radius should be between 5 and 10 meters. Make sure on 1B, if you think they're going fast enough to complete that loop, you justify that answer. You could say, oh, the force total at the top is a positive value. Your centripetal acceleration is bigger than 9.8 meters per second squared. You've calculated the minimum velocity to complete the loop, and it's going faster than that, okay? There's any number of ways you can answer 1B. Whatever you do, just don't say, well, yeah. Well, why? Kind of the gut feeling. Okay? Make sure that you give some type of justification for it. Your answer on number 5 would make an GPA. Okay, anything else? Are we good? Going once? Going twice? So stop that. Okay. So now we've completed the centripetal motion part. So now I want to roll this into things up with gravity. But before we get to that, you have to understand the history of astronomy and kind of where we are and how it works and all this stuff. Okay? Because if you don't understand the history, then the laws don't make any sense. So if you look at any branch of science that has the deepest history and the things that we've screwed up the most, without doubt, it's astronomy. Okay, we've done some really, really stupid things in astronomy. So, and this goes back even to the Greek philosophers, the ancient Greeks. And the question is like, what type of solar system do we live in? So basically, you have two arguments. You have a geocentric, and then you have a heliocentric, okay? So geocentric means earth-centered. So this is like the freshman mentality. The solar system revolves around us, okay? We're special, okay? Everything moves around us. And it makes us feel good, okay? It's like, yeah, we're it. Everything moves around us, okay? And it's like I said, it's like a freshman. It's like, oh, the world revolves around me. No, it doesn't. So there was also like a biblical basis for this argument, okay? You know, God made, if you go Old Testament, God made man in his likeness, put him in the universe, and, you know, all this stuff, okay? And it's also based upon observations. So if you look at a simple example, let's say, all right, next Saturday morning, we're going to spend the day making observations about the movement of the sun. Saturday's supposed to be really easy. So we're going to meet out in the parking lot about 6:30, you know, make some breakfast burritos, maybe some pancakes or something, have breakfast. And we're going to see this big ball of light rise on the eastern horizon. It's cool, okay? Oh, the sun's rising, okay? And then we're going to keep track of what we see throughout the day. And you're going to see this big ball of light move across the sky, and about noon it's going to be here, okay? And we'll have lunch, you know, maybe order in some pizza or something, okay? And then afternoon, maybe we'll play some football or something, and soccer, okay, whatever. We'll watch the sun go down, okay? The sun approaches. We'll fire up the grill, have some shrimp, steak, something like that. And we're going to see the sun set on the western horizon. And I said, what did you all see? And you're going to say, you know, we saw this ball of light appear on the horizon, and we saw it track across, and then it's going to come back down, okay? So it would be similar to if you could take a snapshot of this rubber stopper as it goes around, okay? Because you're stationary, and you see that rubber stopper appear here, and then it goes across, and you see it set over here, okay? That's what you see happening. Goes around, boom, goes around, boom, goes around, okay? And that's what you observe. And it's cool, right? And I said, do you get the sensation that you're moving? It's like, now we're standing out in the parking lot. I'm not moving. You very much get the idea that the sun is moving around you. So that would be analogous to me starting over here and walking across and ending up over here. And I said, what happened? And you all would say, you know, where can't you walk from one side of the room to the other? We saw you move. And I would say, no, I never moved at all. I was completely stationary. You all moved around me. Okay, I never moved. You all spun. But that's a similar type of discussion in terms of that perception. So one of the things we need to establish is which direction the Earth spins on its axis, okay? So let's say, here's the Earth, I have a small scale model, and let's say that Marilla is the sun, okay? So we're looking down on the top of, here's the North Pole, okay? And
where's Kansas?
right here on the equator of Africa. That's why I honest to God, you should have to pass, like, as you know, I always read names at graduation. I think I should be able to ask you a simple question before I give you the diploma. It's like, what's 10% of 50? If you can't answer that, I'm sorry, we have failed you.
He
Okay?
also didn't know what countries bordered the U.S., so. That makes sense.
Geography is not his strong suit.
Well, if he thinks Kansas is in Africa, that's a whole new ballgame.
Yeah.
So I could see where he would
And
be
it had the
confused.
names of, like, I don't know,
The countries.
the countries? Yeah, sorry, my bad, had a brain fart there. It has the name of the country, so he saw Kenya and like, you know, Nigeria and all those, and still thought that Kansas would be.
Kansas, Kenya?
Maybe he's dyslexic.
Okay. Anyway, so back to our story.
What?
So here's the question. If you look down on top of the North Pole, which is up here, okay, Santa's workshop, that'll really piss him up. Okay? Does the Earth spin, as you're looking down on top, does the Earth spin counterclockwise or does it spin clockwise?
I don't know, east or
So how
west.
many vote counterclockwise? One? Counterclockwise.
Wait,
I'll vote counter.
I'll vote counter.
1, 2,
I feel like that makes sense. East or west, never eat soggy waffles.
It's counterclockwise.
4, 5,
Yeah.
6.
Looking at it from the North Pole?
Looking at it from the North Pole. Counterclockwise, clockwise.
Oh, wait.
He lay at the North Pole right now.
I think counterclockwise.
No.
Morella, it's all us.
Counterclockwise.
I think so.
Counter.
Counterclockwise?
Yes.
Is that a vote from you
Okay,
as
what
well?
about clockwise? Okay, well, let's settle the
Let's
argument.
go, Wyatt. Let's go. Come on, Wyatt.
I was soaking
I know we're right.
Why was he
Okay.
in the water?
So here we are, trust me on this one, I'm an expert. Here we are in Maze America, okay?
Yeah.
Amazing.
Now, Morella is our sunshine, okay? So let's start with the basic idea. If we're over here, if I'm on this side, opposite of Morella, what time of day is it?
Nighttime.
Nighttime.
12 a.m.
Yeah, about midnight, right?
Yeah, 12 a.m.
Okay? Midnight.
12 p.m. would be
Midnight.
noon.
I get. Now, if we're here, that's going to be noon, right? Okay. So,
12 p.m. Sorry.
okay. Midnight, noon. True? Everybody
Yes.
cool with that? Those anchors,
Yes.
right? So, let's go with the clockwise group. Okay?
Let's go.
Let's go. So I'm going to stand over here.
Come on, Wyatt.
Okay? And we're going to spin clockwise.
Oh, yeah. Yep.
Okay? So I'm going to come around like this.
Yeah.
Okay? And then we're going to be able to see Morella. Now, if we spin clockwise, I'm looking towards California to see her rise.
Oh, yeah.
Think about it. New Year's Eve always starts in Japan and ends in the United States or something like that.
Yeah. Now, hold on.
It's true. The
Now-
sun rises in
So, like, it has to spin.
The sun
If the
does
Earth
rise.
spins counterclockwise, then I come around like this. Then I'm looking towards the east
Yes.
coast to see her rise. So, to settle the debate, the Earth spins.
Counterclockwise.
Right? Counterclockwise.
We are a
Let's go.
counterclockwise solar system. The planets move counterclockwise, the Earth spins counterclockwise on its axis. Okay? So we got to get that established first. The Earth spins counterclockwise. So, and that kind of matches with what we see the sun doing. Okay, the sun rises in the east and it sets in the west. Okay? So, this whole idea that we're stationary and the sun moves around us makes sense from an observation standpoint. Oh, right. We don't get the sensation that we don't get the sensation that we're spinning at about 400 meters per second, which is what if the Earth is spinning, that's what we're doing, okay? We get the idea that we're not moving, we're sitting here, right? See the sun move, we don't get the sensation that we're moving. Now, let's talk about the moon. So, this is not to scale. Here's our star. Here's our rock. Okay? And we have this companion moon that has 4 possible locations. Okay? And there's like the shadow side, shadow side, shadow, shadow. And this is looking down on top of the Earth. Okay? And we just said the Earth is going to spin counterclockwise. Okay? So visualize this. We're looking down on top of the Earth. And we have 4 positions for the moon. A, B, C, and D. Okay? So when there is a full moon, because if we can figure out the moon, we can use that to model the other planets. So when it's a full moon, where is the moon relative to the Earth? A, B, C, or D?
Are we voting?
How many vote A? Okay. Anybody else vote for anything else? Thank God. Okay.
17
Now,
seconds.
if the moon is at position C, okay, which is where it was yesterday, because there was a partial solar eclipse. If the moon is at C, why can't you see it? There's two reasons. Number one, you're looking at the dark side of the moon, small detail. What's the other problem?
You're on the wrong side of the earth. You know?
That was the loudest, most enthusiastic answer I think you have ever given me.
I was like, I thought that was a really good.
The sun.
Well,
like-
what about the sun?
Drawing the sun is
The
on
sun
the
is
side of
way
the
over
moon,
here.
so you would see the sun and not the moon, I guess
That's
is
what I'm
what she's trying to say.
saying. Like at night you can only see the moon, but you're on the wrong side of the earth.
So it's daytime.
So you'd be looking at the sun.
Yeah.
Yeah,
Pretty much, yeah.
yeah, pretty much, yeah. Okay?
Yeah.
I
So,
don't know.
this is when you have a new moon, which is what happened yesterday, which is why there was a partial solar eclipse, because part of that shadow fell on the earth. Okay, so when you have a solar eclipse, the moon has to be there to cast that shadow. Now, over here, this is when you're going to have a full moon. Now, listen to me very carefully when I ask this question. You want to see a full moon rise, okay? It's like you hear someone talk, there's a full moon tonight. It's cool, let's watch the full moon rise. So what time of day on Earth would you see a full moon rise? Noon, sunset, midnight, or sunrise?
Sunset.
Wait.
Like, it'd be
So here are your options. Noon, sunset, midnight, sunrise.
Sunset.
Sunrise.
Sunset.
No sunset.
I'm feeling sunset.
East to west?
Let me give you a hint. It's either sunrise or sunset.
Sunset.
sunset. It only happens.
Sunset. Why?
It only happens at night
Well, I said
when we're on the opposite side of the sun.
Okay. So if you're standing,
Oh. Yeah,
this
that
is
makes
not to
sense.
scale, but you're standing right here. Okay? So if you're standing right here, remember, the Earth is spinning counterclockwise. So if you're at this point, you would look to the west. You would look to the west, and you would see the sun setting. But then you would look this way, and you'd see the moon rising. Okay? So at midnight, if you're here at midnight, where is the moon going to be? On a full moon, at midnight, where's the moon going to be in the sky?
Straight up.
Directly overhead, right?
Yes.
So then at sunrise, what are you going to see?
The moon in the west.
You're going to see the moon setting, and you're going to see the sun rising. Okay?
In the east.
Makes sense. So, this is why you can sometimes see the moon during the day. So, like for example, let's say the moon is right here, okay, what we call first quarter. So, if the moon is here, if you're at noon, the sun's going to be directly overhead, and that's when you're going to see the moon begin to rise. So when it's first quarter, the moon rises at noon. Then at sunset, you're going to see the sun go down, but the moon's going to be directly overhead. So what happens is that as the moon progresses along here, it rises later and later and later throughout the day until you hit a full moon, and then it rises at sunset. And then when it gets past that, it goes later and later and later. So next week on Tuesday, the moon's going to be roughly about here in its orbit. So what that means is that when we see the sun set, we're going to see the moon over here in the western sky. Okay, so this is going to be important. If an object is outside our orbit, you can see a full view of that. So any planet that's outside of our orbit, Mars, Jupiter, Saturn, you can see a full Mars. Now let's talk about the two interior planets. What are the two interior planets? Mercury and?
Venus.
Yeah, ask your friend that one. Oh, that'll really mess him up. Okay? You can't find it. Whoa. Okay. So, now, why is Mercury called Mercury? Anybody know?
Because it's the fastest and it was like a Greek god.
Yes. So Mercury was the messenger of the gods. Okay. He was the winged foot messenger of the gods. Okay. And so that's why Mercury is called Mercury, because it's the closest to the sun, so it travels fastest. Okay. So the next one out is going to be Venus. Okay. All right. Right. So here's my question. Is it possible to see a full Mercury or Venus like we see a full moon?
I doubt it.
Oh, it's yes or no. It isn't, I doubt. It's either yes or no.
No.
It's always-
Why not?
Because they're in between us and the sun.
Okay? So if Mercury and Venus are here, what's going to happen?
You're gonna see shadows on the sun.
Yeah, you're looking at dark side and you're looking at the sun.
What if they're at like 6 o'clock around the
Oh,
sun?
no, we'll get that.
Oh, okay.
Now, what if they're over here in their orbits? What if they're on
The sun.
way over there? What's the
See
problem?
them.
Big ball of light's in the way. Small problem. Okay? But what if they are here in their orbit? What if they are, so let's say that Mercury or Venus are here in their orbit. Okay, so think very carefully. Mercury and Venus are here in their orbit. You're here, you're seeing the sun set. Where are you going to see Mercury or Venus? Which part of the sky? West or east? West. Because what's happening is that as you go around like this, you're going to see the sun set, and then you're going to be able to look up this way, and you're going to be able to see Mercury and Venus. So if Mercury and Venus are up here, you would see them just after the sun set. Now, what if Mercury and Venus are down here in their orbit?
You see them before sunset.
You see them right before sunrise,
Oh,
because
yeah.
as you come
That's
around
it.
like this, right, you'd be able to look this way, and you'd see them right before you'd see the sun as it came up like this. So that's why Mercury and Venus are known as the morning and evening planets. So, now this could backfire. This is a potential thing that you could do. Let's say that you are dating someone, and you want to kind of test their knowledge of astronomy or science, okay? So it's midnight, right? And you're walking out of a restaurant, whatever, okay? It's midnight. This is going to be important. It's midnight. And you look straight up and you pick a random star or whatever. And you go, hey, look, there's Venus. And they go, oh, cool, right? And if they go, yeah, that's cool, okay? Number one, at midnight, guess what?
Can't see.
You couldn't see Mercury or Venus if you tried at midnight. You're on the opposite side. So if they say, oh, that's cool,
Is Michael Salisbury here today?
no, she's gone.
Okay.
No, well, she's here. She's with bots.
Why complicate things?
I know, but like, what if they're taking attendance, you know?
They're
She's
not.
here.
They're not.
Oh.
They're not. So if your date goes, oh yeah, I see it, that's cool.
Break
okay?
up with them
Idiot.
Now,
immediately.
but this is where it could backfire.
What if are you just gaslighting them? When you're thinking
A little
about
bit.
Venus?
But here's the point. If they have had me for physics, and you do that, they're going to go, you're an idiot. Okay? You are an absolute schmuck. You know nothing about the relative positions of the stars and the planets. So that's your potential downfall. Okay, now, when you judge the positions of the planets, the word planet itself comes from the Greek word which means wanderers. So when you're judging the positions of the planets, what you have to judge off of is like the constellations that are fixed, like Orion, the North Star, okay? The Big Dipper, okay? So it's just like if I'm trying to judge the position of Riley, okay? So let's say I'm over here. So she's here, and I look at her right now, and she's in the constellation roller coaster, okay? Because that's where I judge, because the roller coaster isn't moving. So when she comes in the door, she's first in the constellation phone holder, then she's in the constellation periodic table, then she's in the constellation orange tubs, and she stops in the constellation roller coaster, okay? That's how I judge her position. That's the same thing we do with planets. So the phone holder, the periodic table, the orange trays, the roller coaster, none of those are moving in my room. But you all are. So I can judge your position relative to things that are fixed in my room that I see in the background. So when you're trying to figure out the positions of, this is a cool thing you'll see Tuesday night. So we're going to look at like Jupiter. Okay. When you look at Jupiter, it isn't like we have a range finder when we look through the telescope and, oh, here's the distance to Jupiter, okay? And we get a little digital readout, okay? Or Saturn or the moon, any of the planets. We can't do that. We can look at them, and go, that's cool, but as far as judging where they are, we have to use the constellations in the background. So keep that in mind. Now, here's what I want you to think through. So Tuesday night, when we look out, Jupiter is going to be pretty low in the eastern horizon. Okay, so here's the thing. Jupiter is going to be pretty low in the eastern horizon. So where is Jupiter relative to the Earth? Okay, so here's what I want you to think through. Jupiter is going to be pretty low in the eastern horizon. So that means either Jupiter is out here or Jupiter is over there.
Well, I feel like over there.
Why?
It's not there or there, it's over there.
No.
What? It's over there?
Pretty low in the eastern horizon.
Well, we're spinning
So we're basically
counterclockwise.
seeing like a full Jupiter.
Oh, a full one.
We're going to see basically a full Jupiter. So where's it going to be? Yeah. So what's going to happen is that we're going to be here. We're going to be seeing the sun set, and then we're going to be looking in the direction opposite the sun to see Jupiter.
Oh, yeah.
Okay?
That makes sense. The sun
Right.
sets in the west. Yes.
So that's that check. Now, Saturn, however, is going to be low in the western sky on Tuesday night. So where's Saturn going to be relative to the sun? It's going to be way over here. So Jupiter and Saturn, their orbits are going to be vastly different. Okay? So Jupiter is going to be way over here. Saturn is going to be way out there in its orbit. Okay? What's that noise?
Alarm.
I can stop watch.
So annoying. Okay. So here's the point. If you know where the planets are when they rise and relative to us, you can get an idea of where they are in their orbits. Got that? Okay, so now let's talk some certain players. So when you look at the Greek philosophers, Aristotle, Plato, okay, Socrates, they were all very much into the idea of an Earth-centered solar system. So that was dominant for about 2,000 years. So the first person that really, in modern times, pushed for a heliocentric, helio meaning sun-centered, was a Polish monk by the name of Nicholas Copernicus. So Copernicus, because he worked for the church, really didn't go to get in trouble. So even though he had this beautiful paper, scientific paper laid out, he said, just publish this after I'm dead. Okay, literally, he said, I've got it, I've written it, all this stuff. I don't want to mess with this, so just hold on to it. As soon as I'm dead, then you can publish this paper. So Copernicus was the first one that really came out with a solid paper that said, hey, we live in a heliocentric solar system, which was counterintuitive to what the teachings of the church were. So the next big hitter on this deal, and some of these you just need to see the guy's picture. So when you look at hold on. Oh, go away. Come on. Okay, so Tycho Brahe is one of the more unusual characters in all of science. And we'll choose that one. Okay, number one, he has a great mustache. So Tycho Brahe, if I could go back in time, I would hang out with Tycho. And here's the reason why. So Tycho was of Danish nobility, which means he had a lot of money and didn't have to work. And so he had time to grow this great handlebar mustache. The other thing about Tycho is that, and there's a certain folklore that's associated with Tycho. And this particular picture, notice he has a gold nose. Okay? So according to the legend, Tycho took his math really seriously. And he got into an argument with another Danish nobleman and over how to solve a mathematical equation. And tempers were flared, swords were drawn, boom, lost his nose in a knife fight over how to solve a mathematical equation. They took it really seriously back then. Didn't have anything else to do, so they argued over a mathematical equation. So, in addition to this, Tycho fancied himself an astronomer. So Tycho had his own, he was Danish nobleman. So he had his own island in the North Atlantic, and he built his own observatory on this thing. Now, this is critical that you understand the timing. This is before the dawn of telescopes, okay? So, but what Tycho did is that he built this very elaborate mechanical system, gears and things like that, to keep track of the planets, okay? He didn't have a telescope, but what he would do is he would keep track of, like, oh, how far is it above the horizon? Or how far is it from the North Star? Or how far is it from the belts of the three stars that make up the belt of Orion? So he had exact locations of the planets. And he did this for decades, okay? So Tycho was the keeper of the data, okay? This is important. Tycho had the most extensive set of astronomical data that existed anywhere. Now, you have to keep in mind, this is in the 1600s. It isn't like he had this thing on a flash drive, okay, or an Excel sheet. These were written down in books, okay, in his handwriting. All these volumes upon volumes upon volumes of books. Okay, so that's Tycho, gold-nosed guy, big handlebar mustache. So that's player number one.
Does he have a neck?
Yeah, he does, but it was just always, covered up.
Looks like he's wearing a neck.
Dime.
Was it Tycho or Galileo that got a deer drunk at a party?
Supposedly that was Tycho.
You got a deer drunk?
Yeah, a reindeer. It's an
Yeah.
unfortunate
And
story.
it fell down some stairs and died.
Yeah, just let that go. Not part of the story, part of the folklore, but yeah, that was very much Tycho.
Anymore.
And he had, I can't remember the reindeer's name.
Oh,
Okay.
he did have a name.
Yeah, it did. All right, now, here's the next big player, and that is,
Picture.
Kermit. Kepler? I've heard of him.
So there we go. All right, so here's the next big hitter, and that is, what's a good picture? There's that. Okay? So you got a picture of Johannes Kepler. So Johannes was kind of a weird guy. So Johannes was of the belief that his foremost idea was that there was a mathematical relationship to describe the motions of the planets. So in his mind, this was like a calling from God. Like he was placed on Earth on a mission from God to develop the laws to describe the motions of the planets. Okay, so he was known as the wandering mathematician. So what happened is that Tycho has all of this data. Kepler goes, I'm on a mission from God. So he shows up and actually hangs out with Tycho and says, hey, word on the street has you have all this good data. Tycho goes, yeah, I don't mean to brag, but yeah, I got some. Got some gold nose bling too, but that's not part of the story. So they actually worked together. And so, because Kepler knew he had to have years and years and years and years and years of data to come up with a mathematical way to describe the planets. So here's one of the most intriguing aspects or stories that exist in all of science. So there's various stories, versions of this. Here's my favorite version of the story. So Kepler needs the data. He tells Tycho this, like, hey, I'm on a mission from God. I need your data. So according to the legend, Tycho says, upon his deathbed, that should I have not lived in vain, let Kepler have my data. Because he knew the importance of his data and what Kepler was going to do with it. So Kepler hears of Tycho's passing. He shows up in the castle, knocks on the door. Hi, I'm on a mission from God. I need the data. And again, these were like books, volumes of data. This wasn't like Mission Impossible where he could like download a file or hack into the system. Okay, these were books. So according to the legend, Tycho's family says, no, we're going to go ahead and hold on to this, kind of a family heirloom thing. Okay, we're not going to let you have it. So at this point, Kepler has a moral dilemma because he's going, I'm on a mission from God. This is why I was put there. He goes, just like a songbird was put on the earth to sing, I was put on the earth to do calculations. Okay, so this is what he thought he was destined to do. So he goes, because Kepler knew he could not live long enough to collect the data and do the analysis. He had to have the head start of the data. So, according to the legend, it's kind of a Mission Impossible thing. Kepler breaks into the castle, gets the data, and leaves and goes back to Germany with the books. Okay? So, one of the greatest mathematical relationships to describe the universe was done with data that was stolen from a dead guy. Okay? But, so Kepler gets the data, and he's poring over this. And now, you got to keep in mind, this is in late 1500s, early 1600s. Kepler didn't have a calculator, didn't have the internet, didn't have Oreo cookies, nothing. Okay? He's doing all this by hand. So the first thing he tried to do was figure out, okay, what's the motion of the universe? He wasn't even completely sold on whether we're a geocentric or a heliocentric. Okay? He thought the Copernican system was right, which was heliocentric. So what happens is that Tycho starts to look at the data, and one of the things that you have to be able to describe is something known as retrograde motion. So if someone listens to retro music or they dress in retro style, what does that mean?
Vintage.
Vintage, old school, right? So planets go through what's known as retrograde motion. Okay? So what happens in retrograde motion, and here's the best analogy I can give, is that I'm sitting here and I see Riley in the constellation roller coaster. Okay? So when I'm Kepler and I'm looking at data from Tycho. So what's happening is that over a period of time, I see Riley moving, and this is very small movements. Okay, this isn't like grandiose movements within a night. This is very small incremental movements. So I would see Riley relative to the roller coaster constellation. She's moving in a particular direction, okay? Then all of a sudden, Riley stops moving relative to that roller coaster and starts moving in the opposite direction. Now, she's still rising in the west and setting, still rising in the east, setting in the west, okay? That part's still true. What's happening is that she's moving in the opposite direction relative to a constellation. That happens for a couple of months. And then all of a sudden, she's going to stop, and then she's going to start moving in the direction that she was. So imagine I see Riley moving to my left, she stops, she moves back to my right, she stops, and then she moves back to my left again. Okay? What happens? So in the geocentric model that says here's the Earth and everything revolves around us, it's the ultimate freshman mentality. Okay? We're saying here's the Earth. So, for example, Mars. Mars is moving along, and then it goes into what's called an epicycle. So this epicycle is this small little loop, a suborbit that goes around. So we would be like, Riley is walking this way, and then all of a sudden she goes and she walks around in a loop. And then she comes back, and then she starts going like this. And if she's doing that, that's what I would see. I would see Riley go until she hits the constellation roller coaster, and then I would see her go back until she hits the constellation orange tub, and then I'd see her go back again. So these epicycles were used to explain retrograde motion. And they worked beautifully. Okay? They did. Because Tycho had such phenomenal data, you could predict, oh, Mars is going to go into retrograde. Okay? And sometimes you'll see, like, I have people, like, send me pictures of, like, T-shirts, and it'll say, like, Mars is in retrograde, you know, or something like that. It's like, oh, shut up. Like, people justify their behavior based upon motions of the planets.
Mercury's in retrograde.
Mercury's in retrograde.
I was like, Mars.
Yeah, Mercury. Okay, well, they all do it. So, but here's the problem. It's just jacked up. It's like you're going to tell me this planet is going along, all of a sudden it gets pulled out of its orbit for like 2 or 3 months, and then all of a sudden, nope, it's going to go back again. Okay? It just was not tight. But so no matter what the system was, heliocentric, geocentric, and Tycho actually had his own system. His was a blend of the two. It was called the Tychonic solar system. He kind of blended heliocentric and geocentric. So Kepler takes this data, and how Kepler explains it is that imagine Riley it's like a race. And Riley is on the outside going like this. I'm on the inside going like this. But I'm on the inside, so I'm going faster. So what happens is that as I pass Riley, I change my perspective because I'm on the inside passing her. So what they found is that retrograde motion only happened when you would see like a full Mars, because what happens is the Earth was passing them on the inside. So Kepler crunches all this data, and he does some phenomenal work. So to give you an example of some of the difficulties that he ran into, and this is just a small, simple example. Let's say here's the sun, here's the Earth, and here's Mars, okay? So if this is a situation, when is Mars going to rise? If you're on Earth, what time will we see Mars rise?
Sunset.
Sunset, right? Because here you are, this is like looking at a full moon or a full Mars. So you would see Mars rise at sunset. You would see it set at sunrise, okay? So if you're on Earth, you're looking, and let's say, here's the belt of Orion, okay? Just to make a common constellation. So Mars looks like it's in the constellation Orion, okay? So it takes roughly about 2 years for Mars to get back to that point, okay? So Mars returns back to that same point. Mars completes one orbit. But here's the problem. Earth at that point might be over here. So even though Mars is back to the same point, now if you're on Earth looking at Mars, it's going to look completely different. So it was like Riley's here, and right now if I look at her, she's in the constellation Fawcett, Silver Fawcett, okay? Riley doesn't move. But if I'm over here, now Riley is in the constellation, Track Wall, okay? If I go over here, she's in the constellation Light Blue Shirt. So even though Riley hasn't moved, my perspective on her completely changes because I'm going to see her completely differently. So that became the challenge of Kepler. And this is why he had to have years and years and years and years and years and years and years of data, was to be able to say, okay, even though Mars is back and it's going to look completely differently, I got to be able to compensate for that. Here's the other problem. His platform, the Earth, is spinning on its own axis. It's also going around the sun. The Earth is also speeding up and slowing down because we're in an elliptical orbit, which we'll talk about in just a second. So he has all of these things going against him. But what he was able to do was triangulate the motion of Mars based upon the relative position of the Earth and Mars and where it was in different years. So what he was able to work out was the path of Mars. Because it isn't like, again, when you all Tuesday night, when you all look at Jupiter, it isn't like this is a rangefinder on the golf course and we're going to look and we're going to see a number off to the side that says, this is where it is. Not happening. So here's the deal. So Kepler comes up with 3 laws. And this is what's on those lecture notes that I gave you. Okay? And the first law seems innocuous, but it actually created quite a stir. The first law is the law of ellipses. Now, you all studied math, and what do you know about an ellipse? How many foci does an ellipse have? 2. So an ellipse is basically a jacked up circle. Okay, it looks like an egg. You have 2 foci. So what he figured out is that planets move in ellipses. Sun is at one foci, the other one is a point out in space. And you would think, how could that be controversial? Here's the problem. They viewed the heavens as the realms of God. And the circle was viewed as the perfect geometric shape, okay, which is why it's a wedding ring. Okay, love has beginning and has no end. All points are equal distance from the center. It's perfect, right? So when Kepler comes along and says, planets move in ellipses, it's just like God was trying for a circle and he had an off day and we ended up with an ellipse. It's like, okay, that's problematic. So literally, people were upset about that. It's like, no, they have to move in circles. And Kepler's going, you can think that all you want. Here's the proof. They move in ellipses. Here's the second thing. The second law is law of equal areas in equal times. So, in equal times. So what Kepler did, and this is where the math got real ugly, real fast. So he said, all right, here's the sun, here's the path of Mercury. And once he figured out the orbital radius, what he did is he calculated the area swept out during a certain period of time, okay? Maybe it was 30 days. So what he would do is he would know where Mercury or Mars was at this point in time, and then he would know where Mars was 30 days later. And he would know the radius. So it became a calculation of part of the area. So he would say, this is the area swept out in a 30-day period. But that doesn't make any difference. I just picked 30 days. Okay? And then he came out here and he said, okay, and when it's at the opposite extreme, this was also 30 days. But what he found is that these 2 areas are the same. So the only way that can happen is if you change the arc length of the circle. So here's all I want you to remember out of the second law, is that the only way this works is when you have a smaller radius, you have to move faster, okay? So as this planet moves in this elliptical orbit, the closer it gets, the faster it goes, because this is going to travel a greater distance in its arc length because it has a smaller radius. Out here, you have a bigger radius, so that means you have a smaller arc length. So here's all I want you to remember out of the second law for now. Shrink the radius, you go faster. Increase the radius, you go slower. So it's kind of like if you've ever, let's say in your house, you have like a set of stairs and you have like a banister.
I'm so sorry, can I have Topher for your looking video real quick?
Yes.
Okay, thank you.
So imagine that here's the banister going by the bedpost, and you're in socks, and you run up and you grab a hold of that banister and you like slingshot yourself around. Anybody ever done that? No. Know exactly what I'm talking about. Okay, so this is what's happening. The sun acts as like that banister, and the planets reach out, grab a hold of it, and they slingshot themselves around. Okay? And then they go out and they build up energy and they come back really fast. Okay? Got that visual. Okay. Third law. This is the most challenging, the one that's mathematical. So, this third law, and again, these are laws, these aren't suggestions, these aren't, well, maybe, I don't know. Okay? And this is what's on your equation sheet. Okay? So what this says, this is important. These are going to be the orbital periods. That didn't take long.
They took a picture, and apparently they know nothing about soccer, so they had to ask me what I was doing in said picture.
Okay.
I was kicking a ball.
Good. That's all that matters. That's kind of what you do in soccer. Okay. So when Kepler did this, this was a ratio of the periods of the planets. Now, listen to me. This is a ratio of their orbital radii. These were ratios. These were ratios, which means that it didn't matter what the units were as long as they were the same. So this is the only time I will ever tell you this in this class. This is the only time I will ever utter these words. The units don't matter. Okay? It's the only time I will ever tell you this. They just have to be the same. It could be years and years. It could be days and days. It could be months and months. It doesn't make any difference. They just have to be the same. Now, the radius part, that was tough. It isn't like Kepler could ask his phone, like, hey, what's the distance from Earth to Mars? Okay? Didn't have those numbers. So what he did was that he used a ratio every time that he could. And now, if you're Kepler and you're doing all these calculations, what is the favorite number that you can use? No, not zero. One. You're gonna use the numeric value of 1 every chance you get. So Kepler says, okay, here's the sun, here's the earth, I don't know that distance. So he was clever, he goes, I'm just gonna let that equal 1. So that distance from the sun to the earth is 1 AU, okay, which was 1 astronomical unit. He didn't know the distance, he just said, oh, this is 1 astronomical unit. Which means the distances to Mercury and Venus were less than 1 astronomical unit. The distance to Mars, more than 1 astronomical unit. Okay? Cool with that. So, in terms of how you actually use this, it's easier if you cross multiply. If you start off with this, going the period of a squared times the radius of b cubed equals the period of b squared times the radius of a cubed. Now, let's say we want to compare Mars and Earth. So you're going to have 4 variables. You're going to have the period of the Earth, radius of the Earth. You're going to have period of Mars, radius of Mars. If you're clever and you're Kepler, what are you going to let the period of the Earth be? 365 days or 1 year?
1 year.
1 year. Okay? 1 year. Boom, there you go. It's 1 year. Radius of the Earth. What do you know that be?
1 AU.
1 astronomical unit.
Oh dear.
Okay? Now, let's say that he measures it and he finds the period of Mars to be 1.7 years. And he wants to find the radius of Mars. Now, so here's what you've got. Period of the Earth squared times the radius of Mars cubed equals the period of Mars squared times the radius of Earth cubed. Well, conveniently, what's the period of the Earth? 1 year. So this is just 1. What's the radius of the Earth?
1.
That's cool, right? So something now that looks horribly complicated simplifies down to the radius of Mars cubed equals the period of Mars squared. Now, you can do this, listen to me, you can do this only if 2 of the values are equal to 1. But when you're doing problems like this, start off by laying out all 4 variables. And if you're clever, and you can do this, you can't always do this, but a lot of times you can let a radius and a period have values of 1, because again, this is just a ratio. So what you would do is that you would take the period of Mars, and you would square that. So, and then to get the radius, you would do the cube root. So imagine this. This is without a calculator. You are squaring 1.7 without a calculator, which isn't bad, it's just 1.7 times 1.7. But then you're trying to find the cube root of that value without a calculator. That becomes the tough part. Okay, so stop that. Okay, so this green sheet, this is just all Kepler's laws questions, okay? So when you get to, and I give you this big hint like on question number 5, Jupiter's 5.2 times farther from the Earth than it is from the Sun. Determine Jupiter's orbital period. And I tell you, hint, that the orbital radius of the Earth be 1 astronomical unit, let the period of the Earth be 1 year. So again, on all of these 5, 6, 7, 8, 9, you're going to use Kepler's third law. Okay? When in doubt, lay out all 4 variables. Period, radius, period, radius. Okay? It doesn't make any difference which one's on top, as long as it's the same. Now, Kepler's laws only work with things that orbit the same center. So we could compare the period of Earth and the period of Mars, because they both orbit the sun. We could not compare our moon to a Galilean moon, which orbits Jupiter. Okay? So those orbit Jupiter, our moon orbits us. So I can't compare moons that orbit different planets, but I compare, if you look at like the 4 Galilean moons of Jupiter, I can compare those ratios because they all orbit Jupiter. Okay? So keep that in mind. The other thing that you want to do by tomorrow, so we can start this next lab, this is a polar graph. Okay? And it starts here at 0, goes around back to 360. This is data for the motion of Mercury. So what you want to do is plot these points on this graph. Now, what I would recommend, if you look on most of this data, it's generally between like 0.3 and 0.4. What I would recommend is that you take like maybe like a marker or something and color in that 0.3 and that 0.4 line, because it's just going to make it easier to see. You don't have to, but just a word of advice, or a highlighter or something. So what you're going to do, like you're going to go to October 1st, orbital radius of 0.319 and 114 degrees. So you're going to go, here's your graph, you're going to find 114 degrees, which is over here, and then you're going to go 0.319 around like that, and 114 degrees. So you're just going to keep going around like this. You should get, oddly enough, an elliptical orbit. Okay? Shocking as that may be. So tomorrow you need green sheet done and you need the points plotted. And then that'll start the next lab that will start tomorrow and finish up on Monday. So there we go. Green sheet due tomorrow. I know there's not a backside to it. Okay. Stop you on the camera.